right, let's get started.
I know.
Welcome to the High Energy Seminar. Today our first speaker is Foord. She's a finishing grad student at the University of Michigan, Ann Arbor, where she's working with her advisor, Oklopcic, on dual AGN. Adi got her bachelor's degree from Boston University, where she did a thesis on outbursts in gamma-ray bright quasars, and she's worked on a couple of other topics also related to supermassive black holes. She's also been the PI of different observing proposals from radio to X-ray. And today she's going to be telling us about quantifying the rate of dual AGN with Baymax.
Great, thank you. Can everyone hear me okay? Yeah? Okay, great. So as Francesca noted, my name is Foord. I'm in my final year at the University of Michigan as a graduate student, and today I'm going to be talking about my efforts to quantify the rate of dual AGN using Baymax. Baymax stands for Bayesian Analysis of Multiple AGN and X-rays, and it's a tool that I've developed as part of my thesis. Baymax is also a friendly robot in the Marvel universe, if anyone is familiar with this, but if not, that's fine. So I'm first going to be talking about some motivation for why we need Baymax, and then talking about some of the nuts and bolts behind how Baymax works, and then I'll be showing you guys some of our most recent results using Baymax. So Baymax is mostly going to be studying the dual AGN population. So in the context of galaxy mergers, when you have two massive galaxies, each with their own central supermassive black hole, here they're in the process of merging. So during the phase of the merger where you have two supermassive black holes, they're both actively accreting. The physical separation here is on kiloparsec scales, and the main mechanism of energy loss is through dynamical friction. You can classify the system as a dual AGN system. So we believe that dual AGN are a result of galaxy mergers, and we know that galaxy mergers are quite ubiquitous in our nearby or visible universe. However, to date, the number of dual AGN that have been confirmed remains relatively small, so around 30 or so. Studying dual AGN is important for so many reasons. So it gives us insight on supermassive black hole growth and accretion, as well as the host galaxy's growth and accretion, and how those two are possibly tied. As well, dual AGN are the progenitors to the gravitational wave signals that we expect to detect with PTAs in the future, pulsar timing arrays. So we really want to expand the known population of dual AGN, and we also want to start learning more about their preferential environments and characteristics. So as of right now, most observational evidence for dual AGN relies on optical spectroscopy and photometry. So the most popular method is looking for double-peaked narrow emission lines, which I'm showing you here. So the idea behind this indirect detection technique is that if you have two galaxies, each with an AGN that are in the process of merging, if you take a spectrum of the system before their respective narrow line regions are overlapping, you may expect to see double-peaked narrow emission lines. You can expand on this analysis and actually spatially resolve where each emission component is coming from. And with that, you can then see if the emission coincides with two galactic nuclei, for example. There are some caveats to this technique. So, for example, we do expect double-peaked emission from things beyond just dual AGN, such as outflows or just disk kinematics. So for any dual AGN that is found using this technique, you really want X-ray observations in order to confirm the true nature of the source. So the idea is you can confirm a dual supermassive black hole system if they're both actively accreting and if you have the necessary resolution. So here you're trying to directly detect the emission associated with each supermassive black hole. So if you're going to be using X-rays to do so, you really want Chandra for its superb angular resolution. So this is an example of a dual AGN that was found by Mike Koss using Chandra. So those sorry, can you see these two red detections are the two Chandra detections, and it's being overplot on the optical image. So you can see that the Chandra detections nicely coincide with two optical cores. If you compare this field of view to XMM's field of view, you'll see why for this case it was necessary that you have Chandra to find the source. That being said, Chandra was only able to find this source because the angular separation is around 6 arcseconds, which is much larger than Chandra's nominal resolution of an arcsecond or so. And so unfortunately, as the separation between your two AGN nears Chandra's instrumental PSF, which is around an arcsecond, it's going to become very difficult to detect them even with Chandra. So this is an example of a simulation of a single point source as seen by Chandra on the left-hand side, and a dual point source simulation as seen by Chandra on the right-hand side. And the separation for this simulation is 0.3 arcseconds. So as you can tell by eye, it's very difficult to discern which is the single point source and which is the dual point source system here. So this was really the motivation for Baymax. We wanted to create a quantitative and statistical method to analyze Chandra observations and determine the likelihood of whether it was composed of 1 or 2 point sources. So Baymax allows for this statistical analysis, and it does so using a Bayesian framework, so namely Bayes factor. Bayes factor just represents the degree to which you're favoring one model over another. So for our dual AGN analyses, we're comparing a single point source model to a dual point source model. And within each of these integrals, you have your likelihoods, and then you have your prior distributions. So values greater than or less than 1 will tell you which model is favored, and the magnitude of that value will tell you how strongly the model is favored. So for all of our analyses using Baymax, we do tests in false positive space to better understand what a strong Bayes factor is for a given observation, and it will depend on things such as the total number of counts you have, etc. So the main components of the code are as follows. The first step is to generate likelihood models for single and double point sources. This is done by simulating a PSF that's unique to a given Chandra observation and parametrically fitting it. The next step is to define your priors. So these can be either user-defined or non-informative, but Baymax is flexible enough such that you can incorporate information that complementary optical or IR observations may give you. The next step is to calculate Bayes factor. Baymax does this using a technique called nested sampling. So this is a semi-MC sampling technique that allows you to more densely sample from regions of high likelihood space. So if you remember, Bayes factor is a ratio of integrals, and the number of dimensions that you're integrating over equals the number of priors that you have. So for a given model, if you have 5 or more priors, computationally it'll take a lot of time to calculate those integrals. And so nested sampling allows us to calculate Bayes factor on the order of minutes instead of years. And then lastly, using PyMC3, the maximum likelihood of parameters such as the separation and the count ratio, which represents the number of counts that the secondary has with respect to the primary, as well as their uncertainties, can be estimated. So this slide really nicely exemplifies the power of Baymax, and it allows me to quiz my audience. So I have 10 simulations here. 5 of these are single point source systems as seen by Chandra, and 5 of these are dual point source systems. And I like to see if anyone can correctly identify the dual point source systems. But a lot of time it's quiet. Yeah, did someone say 8? So the idea here is that this is rather difficult, right? So here I'm showing you which of the simulations are actually dual point source systems. So Baymax was able to correctly identify each of these systems as dual point source systems. So Baymax works quite well both in the low separation and the low count ratio regime. So if you look at panel 1, for example, the separation here is quite large. It's an arcsecond, but the count ratio is 0.1. So with 100 total counts, that means the secondary is contributing around 9. If you look at panel 3, the count ratio is higher here, so it's 0.6, but the separation is smaller than 0.5 arcseconds. So in general, to probe the lower separations, you'll need a higher count ratio and vice versa, and that will, of course, also depend on the total number of counts that you have. Okay, so I've talked a little bit about motivation and the nuts and bolts, and now I want to start showing you guys some of our most recent results using Baymax. So thus far, we published, or at least published one and submitted a second paper using Baymax on various systems. So the first paper was using Baymax to study, at the time, the lowest mass dual AGN candidate. This was a dual AGN candidate based on archival and shallow Chandra observations. So this is, on the left-hand side, I'm showing you the raw 2 to 7 keV Chandra observation. When you bin and smooth that observation, it looks as it does on the right-hand side. And so that slight extension in the northwest direction is what made people believe it was a dual AGN candidate. This ended up being a non-detection, and so I'm not going to be focusing on this analysis, but I urge you to go read the paper if you're interested in learning more about the methodology and the statistics behind how Baymax works. So now I'm going to be focusing on this second analysis that we recently just submitted. Baymax analyzed a sample of 12 dual AGN candidates. So each of these systems were dual AGN candidates based on narrow-line O3 emission that was found in their SDSS spectra. So that's using that indirect detection technique that I spoke about on my first couple of slides. And so each of these systems then received follow-up long-slit observations, and what those long-slit observations allowed one to do was spatially resolve where each O3 emission component was coming from. So pairing that information with the X-ray information, we had an informative analysis on the true nature of these sources. So here I'm showing you the optical observations for each of these sources, and in the red and yellow boxes, I'm showing you the location for our informative priors, and that was based on where the O3 emission was found to be spatially resolved. So they all received follow-up Chandra observations, which I'm showing you here. And once again, those red and orange boxes are informative priors for the location of a primary and secondary AGN. I want to note that we also use Baymax using non-informative priors, and so in that case, the primary and secondary were allowed to sit anywhere within this box. So running Baymax on these sources, we found that there were 4 that had a Bayes factor value that favored the dual point source model very strongly. So I'm showing you 2 figures here for each of these systems. On the left-hand side, I'm showing you the unbinned Chandra data. I'm showing you the unbinned data because Baymax is able to probabilistically assign each count to a different model component. So for the dual point source model, your components are a primary point source, a secondary point source, and some type of background contribution. So in the open-faced squares, this only works half the time, but in the open-faced squares are the counts that are most likely associated with the secondary point source. The circles are the counts most likely associated with the primary, and then the triangles are the counts associated with background. For one of these sources, there was this diffuse emission that you see both in the X-ray and in the optical data, and so we had an additional component in the model when fitting this observation to account for that emission, and you can see that in the blue data points. And then on the right-hand side, I'm showing you the joint posterior distributions for separation and count ratio. So because Baymax is able to probabilistically assign each count to a different model component, you can sample from the posterior distributions and actually create many different spectral realizations of each component. So this is exciting because it's one of the first times where we can disentangle counts from a closely separated system and actually fit for their spectra. So I'm showing you an example for one of these systems that had a Bayes factor that favored the dual point source model. This was a system that had that diffuse emission, so you see it both in X-rays and in optical. And in the bottom panel, I'm showing you 1,000 different spectral fits to 1,000 different spectral realizations for the primary point source and for the secondary point source. And I'm overplotting one of those spectral realizations in black. So a spectral analysis is useful for a couple reasons. The first being that with the posteriors that you receive from Baymax, you're only getting the count ratio, whereas with a spectral analysis, you can do the flux ratio. And then secondly, spectral analysis allows you to better constrain the X-ray luminosity of your sources. So what we did is we defined an AGN luminosity criterion of 10 to the 40 ergs per second, and if any secondary did not meet that criterion, we would cross it off our list as not likely being a dual AGN. The idea here being that at X-ray luminosities below that threshold, you're susceptible to contamination from high-mass X-ray binaries and ultraluminous X-ray sources. So returning to our 4 systems, we did this spectral analysis, and we ended up finding that there were 2 that had a primary and secondary that met our AGN luminosity criterion. One of these systems was the merging system that had that diffuse emission, and so we had an additional component in our analysis where we compared the spectra of the secondary to the diffuse emission, and we could not distinguish between the two at a high enough confidence level. And so conservatively, we crossed that system off our list as well, and we ended up with one dual AGN. So in addition to the X-ray analysis, you can use complementary multi-wavelength observations to try to learn more about the environments and characteristics of any dual AGN that you find. So starting with our sample of 12 systems, 6 were visually identified as merging in the optical data. And of this subset of 6 systems, it included the 2 that had a primary and secondary that met our AGN luminosity criterion. And those 2 data points are circled in blue here. So one thing that we looked at, for example, was how the separation between the galactic nuclei varied or just versus the extragalactic hydrogen column density, which is a parameter you can fit for using the X-ray spectra. So I won't call this a trend because I acknowledge that we only have 6 points, but I will say that the data suggests that dual AGN pairs may prefer closely separated gas-rich environments, and this is something that simulations have found as well. In the future, I hope to obviously have a much larger sample, and these are the types of things that we want to look at to find any possible trends in the data. Okay, I also wanted to note that you can use Baymax for a lot more than just dual AGN. So as long as you have an analytical description of 2 models, Baymax can calculate the Bayes factor. So most recently, Baymax was used in a study looking at C and B quenching of high-Z radio galaxies. This is a project being led by another graduate student at the University of Michigan, Kate Napier. And on the left-hand side, I'm showing you a radio observation of this high-Z galaxy she's studying. So you can clearly see there's a core as well as 2 radio lobes. One of the questions that Kate had was, are the lobes emitting in X-rays as well? And if they are, what is the X-ray luminosity? So when you look at the Chandra image of the source, because you only have 56 counts, it's very hard to tell whether there's any sort of extension, and if there is, if it has the same position angle as the radio observation. So I ran Baymax on the Chandra observation. Here I was comparing 3-point sources to 1-point source. And because I had the radio data, I had informative priors for the location of the core as well as the 2 lobes. So Baymax strongly favored the triple point source model when I did this. And here, once again, I'm showing you a plot of the unbinned X-ray data where each count has been assigned to a different model component. Also, I just wanted to highlight that you could use Baymax to study multi-AGN systems. So SDSS J0849 plus 114 is a system that's been getting a lot of press recently. This is a triple AGN system. It's a project that was led by Ryan Fiefel at George Mason University. This is a figure taken from his plot on the left-hand side, where you have the SDSS image in the lower left-hand corner and the HST image in the center. I'm showing you the Chandra image on the right-hand side. Once again, I ran I ran Baymax on the Chandra image. Here, I was once again looking if it was better fit by 1, 2, or 3 point sources. The triple point source model was strongly favored. And here I'm just showing you the joint posterior distributions for the 2nd and 3rd point source, as well as, once again, the unbinned X-ray data. So what I'm currently doing is analyzing a larger sample of triple AGN that I found throughout the literature that all have archival Chandra data, and I'm trying to find more triple AGN systems. So look out for that. Lastly, I just wanted to talk about a future analysis that I'm excited for. I want to use Baymax to quantify the rate of dual AGN across cosmic time. So as of right now, there's no well-constrained measurement of the fraction of dual AGN as a function of redshift. So what I'm showing you in this plot are results from Eagle simulations looking at how the dual AGN fraction varies as a function of redshift. They found this trend where it seemed to increase as a function of redshift. But the gold star in the upper left-hand corner is our nearby observational constraint. So you can see that there's a huge mismatch between the simulations and the observations, and you can also see that observationally we haven't been able to quantify the rate as a function of redshift or at higher redshift. So this is something that I want to do using Baymax on all of the archival Chandra data that's available, so the deep and wide public fields. So if you use these surveys and you make a couple cuts, like off-axis angle, because the Chandra PSF becomes quite distorted as a function of off-axis angle, as well as some threshold for a number of counts that you want to analyze. I have over 700 AGN that I can analyze with Baymax over a really wide range of redshift. So the plot looks a little different now, but in the blue I'm still showing you the Eagle simulations, and the star is still the observational constraint. But in red, what I'm showing you is my 700 AGN that have been binned into 5 redshift bins, and the fraction of dual AGN that we expect to measure, as well as error bars on that fraction. I've then taken the blue simulation data and I've scaled it, which I'm showing you in green, such that the dual AGN fraction matches the observational constraint at the lower redshift end. And once again, done the same thing with my data in red. So what this is showing you is that my sample allows us to statistically differentiate between what the models predict and our observational constraint, but we can also really well quantify the rate of dual AGN as a function of redshift in each redshift bin. So this is something I hope to do as a postdoc. So I think I may have gone over my time, so I'll just leave my conclusions up, and thank you so much. Those were simulations. It favored the dual point source model. Yes, yes. I only showed you the ones that Baymax currently identified. Yes.
How much your success at finding correct rule depend on using informative versus non-informative priors?
So
are those priors mostly about the location of the sources, and when you have no information whatsoever about the location, does the result still hold?
Yes, okay, so great question. So for the simulations that I showed you, that panel of 10 simulations, there I was using non-informative priors. Okay, so using informative priors, of course, will definitely, in most cases, lean you towards one direction, which is why it's important to always also run Baymax using non-informative priors and compare what you get. So for the sample of 12 dual AGN candidates that I analyzed, the 4 that all favored the dual point source model did so both using informative and non-informative priors, and the Bayes factor was just stronger using the informative priors. And so it's going to be a case-by-case basis, but we're always going to be doing informative and non-informative and trying to piece together what those results will mean. And then your question about if we're just fitting for location.
Yeah, those priors are mostly on location.
So as of right now, it's location and background contribution fraction, and then the fraction of counts between the two. In the future, I want to start fitting for spectral information as well. So given the XYE of a photon, what's the probability that it's coming from a point source centered here with a spectrum, with a gamma of X, for example. But that's a future step that I need to implement. I have not yet applied it to HRC data, but it should work in the same way. It's flexible so that it can work for HRC as well. Also, I will note that Baymax is flexible such that you could technically use it for any X-ray telescope. So as long as you have a PSF model, it's not just constricted to Chandra. So I do in the future also want to use it on XMM and NuStar, telescopes that have different sensitivities to different energy ranges. But yeah, it should work for HRC.
Is the study publicly available, or are you planning to make it so?
We're planning to make it publicly available, and I'm aiming for this summer.
I have a question about the number of counts. So if you increase the number of counts and have this house with 1,000 counts, let's say, and the other house with 15,000 counts, so they are similar counts. Have you done the tests where you have a limit of resolution between these two concepts? So what we've done is basically created thousands of simulations
with a various numbers of total counts and done different separations and count ratios. And so we have these grids where, given a certain number of counts, you can see where in parameter space you're sensitive to.
And also you can, because you also have counts which mix between the two sources and get to this high count.
Yeah.
Counts in between. Do you assign probability for those counts in between?
Oh, yeah. So the way that the code works is that each count has its own probability given its XYE. Yeah. Yeah.
Is the code generally useful for distinguishing diffuse readings between real point sources?
So, yeah. So I showed you one example of that source that had that diffuse emission. So we've done a lot of tests just because we had a paper that had a source with diffuse emission. It usually does pretty good. It might become more complicated if your diffuse emission isn't spatially uniform, for example. So you need to start, implementing your own models of how you believe the diffuse emission, spatially sits. But it so far has been working quite well with all of our tests.
So I guess this kind of thing could be expanded well beyond two expected point sources to
Yes.
clusters or to nearby galaxies.
Yes.
Or whatever.
Yeah, if you have a model, so it doesn't have to be a point source. You could have a model for some type of diffuse emission, like with an exponential profile, for example. But as long as you have a model, it will compare two models to one another. You just have to have a way to describe the components of the model that you believe. Yeah.
Final question? Yep.
Science question. The AGN rate from the simulation, the dual AGN number to redshift, you said something about how that's estimated? Because
Yeah.
with the lustrous, you lose pairs that are less than a few kiloparsecs apart.
Yes. Yeah, so with Eagle, I think the resolution there is the same, so it's about a kiloparsec or so before you lose resolution. What that plot was showing you was the observable dual AGN fraction, so I think both AGN had to have an X-ray luminosity above 10 to the 43 ergs per second, and they had to be within 30 kiloparsec of one another. Like you mentioned, the spatial resolution is such that below a kiloparsec, you lose all information. That might be one of the reasons for that large offset between the simulations and the observational constraint. But once we start using Baymax on the higher redshift sources, we are also going to be sensitive to kiloparsec separations. So in that sense, comparing the two will be pretty consistent.
Any final question? Okay, no, that was great. Thanks.
Thanks so much.
I don't know. I'm pretty sure I've given talks here with this computer and I've never had it.
There are definitely days where, you know, for mysterious reasons, that even the like CF people are like, I don't know what's going on.
Well, thank you for your help.
Yeah, no problem. It was just trying again.
Oh wow. And it will be on YouTube.
Oh, wow. Cut it if you want. And then put technical issues. Can put in a little.